let's consider an application of tensor analysis. So, how do tensors arise in the real world? For here, we'll consider normal modes of oscillating systems. For example, if we have a periodic function in the real line, we could try to express that function as a Fourier series. So we try to write it as a sum of cosines and sines. In this case, the normal modes of the system are just going to be the cosine and sine functions. So we can think of normal modes as being the pure tones for the behavior of the system. In practice, normal modes arise in physics when we study mass spring systems, or other oscillatory behavior, and in chemistry when we study molecular vibrations. For here, we'll focus on mass spring systems. Now to begin, we consider motion in a line. So we'll have two masses, they'll be joined by a spring. The situation here is ideal, so we have undamped motion, so no friction. The only force is going to be the restoring force coming from the spring. At t equals 0, we'll assume the spring is lax, and we'll have initial velocities on each mass. Now, if we run through the differential equations, we note the future behavior of our system is determined entirely by the initial velocities. Now, if we're interested in periodic behavior, note if we have periodic behavior for our system, if I rotate by 180 degrees, we'll still have periodic behavior, although it might not be the same. So we try to exploit the symmetry of the system to break down into normal modes. To quantify things, let's see what we have. Now, we're going to have initial velocities on mass 1 and mass 2. Since we're in the one-dimensional case, these are just going to be real numbers. So we'll call those v1 and v2. We're going to put them together in a 2-vector. Now, if I want to find normal modes, I want to catalog all the group actions that are occurring in our system. So first, we're going to have symmetry in our masses given by the interchange. We note we'll also have a symmetry on the initial velocities. So if I switch 1 and 2, what happens? We're going to switch those initial velocities, but they're going to change direction, so we're going to also have to multiply by a -1. So if we're interested in representations, what we have, our group is going to be a Z2. For the first representation, it's going to be the permutation of the masses. So we'll have a vector space spanned by E1 and E2, each representing a mass. On the identity element, we have the identity operator. And then on the non-trivial element, we'll have the matrix 0, 1, 1, 0. So that just does the switch. On the initial velocities, what do we have? On the identity element, we just multiply by 1, so no change. And if we do the switch, then we're going to multiply by a -1. Then we're going to take the tensor of these two actions. To see the tensor action explicitly, we compute pi1 tensor pi2, evaluate at the non-trivial element 1. So we have 0, 1, 1, 0 multiplied by a -1. That carries the initial velocity vector v1, v2 to minus v2 minus v1. So we switch and negate. Now for the pictures, if I take 1 and 2 and switch, it's going to interchange the velocity vectors, but they're going to be pointed in the opposite direction now. So we multiply by a -1. To find the normal modes, we look at characters. So character of pi1 is two-dimensional. We take traces, we get 2, 0. Pi2 is just a sign representation, so we have 1 minus 1. For the tensor, we take the product, so we get 2, 0. Now, either by applying formulas or observation, we note 2, 0 is equal to 1, 1 plus 1 minus 1. So the tensor product is equivalent to a trivial plus a sign. If I want to find the normal modes, we're going to compute the projection operators for each of these irreducibles. Then we're going to peel off the columns of those operators. Now, for the trivial, what do? We're going to take 1/2, we're going to apply a representation to each group element, and then we weight by the character values of the irreducible. Okay, so here we're using the trivial, so we just put a 1 in front of everything. For the normal mode, I want to use the vector 1 minus 1 for v1 and v2. Likewise, for the sign, Okay, when we wait, we have a 1 and a -1. So for our normal mode, we're going to use the initial velocities 1 and 1. For the pictures, okay, so for the trivial, what do we have? We're going to have initial velocities are equal and pointed at each other. So our picture is going to look like this. So what we have here is just pure oscillation. Okay, these masses are going to move in and out in sync. Note, under the non-trivial Z2 element, there's no change in the picture except for the labeling. For the sign representation, okay, what do we have? We're going to have our velocity vectors are equal and point in the same direction. So this isn't periodic motion per se. Okay, what we have here is just pure translation. If we apply non-trivial element of Z2, that changes the direction of our translation. Now, if we believe what we said about our normal modes being the pure tones, this says that all motion of this system of two masses is given by taking, okay, this pure oscillation and adding it to a translation. Now let's consider motion in a plane. We have the same situation as before, except now we have three masses joined by three springs. As before, the future behavior of the system is determined entirely by the initial velocities on each mass. Now these initial velocities are just going to be given by two vectors. So for the entire system, everything's determined by three 2 vectors, and we put that in a 6 vector. Note, if we consider symmetries, okay, we have rotations by 2 pi thirds, minus 2 pi thirds, and then these three reflections. So our symmetry group is an S3. Okay, we note on the 6 vector, we have the permutations of 2 vectors, and then we'll have the usual action of S3 on R2, so by rotations and reflections. Now, let's consider the tensor product. So for pi 1, that's going to be our permutation representation. For our vector space, we'll have standard basis, E1, E2, E3, and the group acts by permuting the labels. For the action on initial velocities, we'll call that pi 2, this is just going to be the irreducible two-dimensional of S3, so by rotations and reflections. Here, I'll call the standard basis of R2, F1 and F2, to distinguish from this basis. Now, for a sample computation of the tensor, okay, we'll need to do a lot of these, but I'll leave that work to you. Take pi 1 tensor pi 2, apply to the element 1, 2, 3, and I'll apply that to the vector E1 tensor F1. So we apply the group action to each component. In the first part, we're just doing permutations, so that goes to E2. For the second part, we're doing the action of 1, 2, 3 on R2. Now, with respect to the standard basis, we have this matrix here. So F1 is going to go to minus a half F1 plus square root of 3 over 2 F2. Then we can expand this out to get the tensor minus a half E2 tensor F1 plus square root of 3 over 2 E2 tensor with F2. Compute with 6 by 6 matrices. Choose a basis for the tensor product consistent with the 6 vector. Now, to do that, we're just going to group according to the label for each mass. So for the 1s, we have E1F1, E1F2. For the 2s, E2F1, E2F2, and so on. Then, to simplify the notation, I'll label according to the irreducible two-dimensional. So I'll have R, which is going to be rotation by 2 pi thirds counterclockwise in the plane. C is just going to be reflection across the x-axis. Then I'll leave it to you to confirm. For the tensor action, we get the following 6 by 6 matrices. Next, we compute multiplicities of irreducibles in the tensor product. So I set up the character table for S3. We note for the permutation representation, when I take the trace, we're just counting the number of fixed points. So we'll have 3, 1, and 0. Then, for the tensor product, to get its character, we just take the product. So we'll have 6, 0, 0. And if I want to count multiplicities, our rule is we divide by the order of the group, and then take the weighted product of the row for the tensor with the given irreducible. So for instance, for the trivial, what do we have? We're going to have 6 times 1 plus 3 times 1 times 0 plus 2 times 1 times 0. So we're going to have a 166 so the multiplicity of the trivial is a 1. Likewise, we see the multiplicity of the sine is 1, multiplicity of the irreducible two-dimensional is 2. Now, to compute normal modes, compute the projection operators for each irreducible, and then consider the columns. We apply our formula using the 6x6 matrices on the previous board. So for the trivial representation, we note this has multiplicity 1, so any column that's non-zero in this matrix is going to correspond to a normal mode. We compute. Now, for the projection operator itself, we have a weight of 1/6. We'll call the first column V, then we fill in the rest of the matrix with these multiples of V. With that, one can check that we have a projection operator. Then we're going to apply the first column to get our normal mode. Now, we're going to assign each 2 vector in here to our masses as initial velocities. So we have 2, 0, minus 1 square root of 3, and minus 1 minus square root of 3. Note, each vector has the same length. What we have here is a breather mode. So it's going to be uniform, contraction, and expansion. If we apply all this to the sine representation, same idea. Okay, so we're going to get the vector 0, 2, minus square root of 3, minus 1, square root of 3, minus 1. We draw these vectors in, and we know that these vectors are going to be perpendicular to the ones in the previous, okay, for the trivial representation. So what we're going to have here is going to be a pure rotation. So note, there's no restoring force coming from the springs in this example. For the two-dimensional irreducible, we get the projection operator either by applying the formula or by noting that the sum of the projections is equal to the identity. Either way, our matrix is going to have first 2 columns as follows. Now, this representation is multiplicity 2, so I want to find a way to split things up nicely to get normal modes. If we go back to our first example, we note that we had translations. So you'll note we get translations by considering the span of 1, 0, 1, 0, 1, 0, and 0, 1, 0, 1, 0, 1. And then the pictures look like this. Note this accounts for all translations since there's 2 dimensions of translations for R2. Now, to get a normal mode, we'll take our first column vector and then take the part that's orthogonal to these 2 vectors. If we apply our formula for this, guess what do? We take our column vector, we're going to take the dot of our column vector with the first vector, then we divide by the length of the first vector. So we get this vector here. We know with just this subtraction, we get orthogonal to both of the vectors for translations. We draw the picture. What we have here is what we call Pomper mode. So this isn't going to have uniform expansion and contraction. It's going to expand and contract along the x-axis. Now, note, if I apply 1, 2, 3, that's just going to rotate everything by 2 pi thirds, and that can rotate by 2 pi thirds again. So it looks like we have a 3-dimensional space here, but note, if I take the sum of these 3, okay, that's going to send all of our velocity vectors to 0. So 2-dimensional.